Hello, AP Chemistry students, and welcome to AP Chemistry video. This is Mrs. Hanson, and Ms. Schneider and I, we make these small little videos for you to watch on little tiny gems of AP Chem content because we want you to learn this stuff, and then we're going to come in and do the real stuff, which means do the problem solving and do the labs and do the collaborating. So we're going to do exactly that for this topic. So I know you guys know all about the ideal gas law formula, PIVNERT. I call it PIVNERT, PV equals nRT. So pressure, volume, moles, and temp, the four variables that explain every gas, okay? Well, we know how to use that formula, but now we're going to do advanced PIVNERT. Advanced PIVNERT just means we're going to use PIVNERT, but we're going to use it to lead us to some other variables, most notably molar mass and density. Okay, so let's just go ahead and give this a go. We'll start with molar mass. You know already that molar mass is the mass of 1 mole of a substance. Okay? If we put that into a formula, molar mass abbreviated with a capital M would be mass, right, per mole. So that's how you get for the units, grams per mole, right? Okay, so in other words, if you had some kind of sample of a compound or an element, if you had its total mass, whoops, I'm going to switch colors here. If you had its total mass and you knew its total moles, if you divided the two, then you'd have the mass per mole. Okay, and that would be specifically the molar mass. The great thing about molar mass is it never changes for a pure compound or element. So in other words, the molar mass of water is 18.01 and it's never going to change. So you can use molar mass as a tool to identify unknown compounds and elements. Okay, so one thing I want you to know is molar mass is something we're going to talk about here in this gas law unit, but we will tie molar mass probably into just about every topic in AP Chem. Okay, so let's give it a go. So the problem says the density of a gas was measured to be 1.50 atm, so that's a pressure, and 27 degrees Celsius, so that's a temp. And of course, you know in the gas law unit, any temperature you ever come across, you need to convert it to, I'm waiting for you to fill in the answer, Kelvin. That's right. And the density was found to be 1.95 grams per liter. Okay, now when I see that 1.95 grams per liter, what I'm going to do is I'm going to break that up. I'm going to say 1.95 grams is the mass, and my sample is 1 liter. Okay, so yeah, it's a density, but it's also 1.95 grams per every 1 liter. Okay, so now we got ourselves a volume as well. And then calculate the molar mass of the gas. Okay, so we're going to go ahead and use this molar mass formula. We say, alrighty, so molar mass equals mass per mole. Awesome. And I say to myself, well, let's see here. I do have this mass, 1.95 grams. Great. And where's my moles? Okay, and I don't see moles as not given, so that's where PIVNERT comes in. So the second piece to this little puzzle is we're going to take our old friend PIVNERT and take a look. So now we do have the pressure, we do have the temp, we do have the volume, which we set to 1 liter. And let's see, we always know what R is because that's the ideal gas law constant, 0.0821. And hopefully you remember the units. Make sure you include those in your work. ATMs times liters over moles times Kelvin. Okay, and we can solve for moles. So basically it's like a two-step process here. We're going to use PIVNERT to solve for moles. Okay, and then we'll take that mole value and we have the mass and we'll plug it in. And then our second step is to solve for the molar mass. So at this point, I know you guys are aces with algebra. So I would pause the video and I would just go through this process. Okay, so take as much time as you need. And then when you're ready, go ahead and resume and we'll make sure that you got the same solution that I got. So you guys are working through the problem. Hopefully you got yourself a calculator. All right, good times. So let's see, how'd you do? So I like to map out my variables over on the left-hand side. So I had my pressure, my volume, my temp, which I did convert to Kelvin, and I had that mass that we pulled out of the density, okay? Then, I like to manipulate the variables first before I plug anything in. So PV equals nRT, I solve for N by dividing both sides by RT, right? So then I got this new formula, or manipulated formula, and I plug things in. I did want you to see that when you use R, 0.0821, 8 times liter over moles times Kelvin, things cancel out, okay? And I love to see that you guys are showing clear work, and you can see what happens to your units. So the ATM cancels out with ATM, and the last thing we're left with is moles. All right, so even my mole value, I did even take into account sig figs. Oh yes, sig figs are a big thing in AP Chem. So let's talk about that for just one hot second. See, 3 sig figs. This volume really is infinite sig figs because it was from that density that was 1.95 grams per, set per liter. So that doesn't really count for sig figs. Even R, let's see, decimal point present, skip the zeros. We had 1, 2, 3 sig figs. And then 300 Kelvin also has 3 sig figs. Keep in mind there's a little decimal place there. So let's see, decimal point present. These are just placeholders. So I skip those zeros, 1, 2, 3 sig figs. Whew, I know, sig figs, your favorite topic. So that was my mole value. And then I came up here and I went ahead and plug that bad boy in. Okay, so now molar mass equals 1.95 grams, my total grams over my total moles. Okay, and it came out to 32.0 grams per mole. Hey, you might even have a guess as to what substance this could be. I have a guess. How about maybe O2, the air you're breathing, or the oxygen that you're breathing? Molar mass is 32. Okay, so like I said, molar mass is a great tool to identify an unknown compound or element. All right, what do you think? Make sense? All right, I'm going to just throw out a little thought for you guys. Sometimes, here's my molar mass and there's Pivnert. Sometimes people like to take these two formulas and kind of merge them together into one. So in other words, if I take the molar mass formula and solve for moles, then I can just take this guy and substitute in. Hey, you know what? I love it. If you manipulate things, you can solve for molar mass directly. You'll see this a lot in your textbook, even on the internet. It's totally fine, except that this formula is never given. So my personal preference is that, you know what? We always know Pivnert. It's also given on your formula sheet. Molar mass, we know that. That's also given on the formula sheet. Why take the time to merge those two formulas together when you can just use these two formulas as two separate steps? And I think it's way easier. All right. So that's my thought for you. Fun times. Let's continue on. So molar mass is one variable that you can solve for from Pivnert, but going a little further. Density is another one. So density is a measure of how packed the particles are in a substance. Now, the piece about density is that the density of solids and liquids is relatively constant, but the density of gases is totally dependent on the conditions. For instance, I wanted you to see these boxes right here. We always are trying to visualize gas particles. So like this one right here has like 1, 2, 3, 4, 5, 6, 7, 8 gas particles in it. If I double the particles, we would say that this one is more dense. Okay, because the particles are more packed because there's more of them, right? And then also, of course, you'd get a different density in a sample if you had bigger particles. So I just want you to visualize that density is how packed the particles are in a space. Let's see what this math does for us. So density, we kind of understand it conceptually, how packed the particles are. The formula for density, as you well know from whenever, 6th grade potentially, density equals mass per volume, right? All right, so how can you solve for the density of a gas? So it said, what would be the density of carbon dioxide submerged 50 meters below sea level, about 72 psi and 17 degrees, let's say in a balloon maybe, okay? All right, well, let's take a look. So obviously this is advanced Pivnert. So we'll start with Pivnert and we'll say to ourselves, well, let's see, I have a pressure, 72 psi. I have a temperature, 17 degrees. What else do I have? And wow, all I know is that the substance is carbon dioxide. Okay, well, here's the thing about some of these problems is sometimes you have to make some assumptions so that you can come up with some other variables. In the case of density, you can either assume that your sample size is a 1 mole sample or that your sample size is a 1 liter sample. It really doesn't matter which way you do it because whether you assume you have a mole of a sample or a liter of that sample, guess what? The density will be uniform throughout. So it doesn't matter if you have like a glass of water, a bathtub of water, an ocean of water, the density of water is constant. Okay, so same thing with gases. It will be uniform throughout the sample. I'm going to say, in my personal opinion, it's usually easiest if you assume that you have a 1 liter sample. Okay, and then keep in mind, you do also know what the substance is. It's carbon dioxide. And just like we talked about a moment ago, you do know that the mass of 1 mole of CO2, you do know its molar mass. You can look it up off the periodic table. 1 carbon, 2 oxygens. If you add that up, is 44.01 grams per mole. So I think that might come in handy too, and we're going to see how in a minute. So if you want, I would go ahead and give this a try. So let's see. We got the pressure, we got the temp. We always know R, okay, and we just decided that we're going to assume a 1 liter container. Well, now it seems possible that we could indeed solve for moles. Would you agree? Okay, and then, well, what's our second step? Okay, well, just keep in mind that since we assumed 1 liter, this when we get this mole value, that would be the mole per 1 liter. Okay, and keep in mind is density is just grams per liter. So I bet you know a really easy way. Okay, density equals mass per liter or per volume. I bet you know a really easy way to convert from moles to mass. So bottom line is I think I gave you guys enough here. I'd like to pause the video and just give it a go. Okay, start crunching the numbers and see if by the end you can come up with grams per liter as your final answer, the density of this gas. All right. Okay, hopefully you guys had enough time. We've worked through it. Let's see if we got the same answer. Whoops, one more slide. All right. Ooh, one thing I forgot to remind you about is did you convert everything to the appropriate units to match the ideal gas law constant R? So that 72 psi, you had to convert that to ATM. So I'm going to go back. I hope that you guys noticed I gave you guys that same old list of pressure conversions that you used last year. So you can see that 1 ATM equals 14.7 psi. Okay, just remember these are all equivalent. Okay, so you could do a quick little pressure conversion. Okay, so the pressure was about 4.9 ATM. Temperature I converted to Kelvin, and we assumed 1 liter. So we went ahead and solved for moles, right? You guys can see how we worked the algebra magic here. And again, I just love to make sure that everything crosses out appropriately, so I'm left with moles again. All right, so once I got 0.021 moles, and I left that to 2 sig figs to match the 2 sig figs that went in, guess what? I went ahead and just used the molar mass. If this is the moles of CO2 for every 1 mole, 44.01 grams, and I just converted it to grams. So the density of this gas is 9.2 grams per that 1 liter. Isn't that easy? All right, so you guys, that gives you 2 examples. Now, please make sure that you bring these guided video notes all nice and completed and see what we're going to do with this assignment tomorrow during our remote learning lesson. Thanks so much for listening. I hope you have a fantastic day.